Hello and welcome to my channel. This video is a second video on Faraday's law of induction. The first video discussed the case of a rod or a frame moving in a static magnetic field. This video is about changing magnetic fields in time. A few slides to remind you about terminology and concept we used in the first video, the magnetic field and the Lorentz force. The magnetic field is described by magnetic field lines where the direction of the magnetic field is the direction of the arrows and the density of the arrows reflects the strength of the magnetic field. It's a convenient way to show where the field is pointing and how strong it is. When the field is not in the plane of the slide, the terminology is that we draw dots when the field is pointing towards you and X's when the field is pointing away from you, just like the tip and the back of an arrow. The flux is defined as the total number of field lines crossing a unit area. A reminder about the Lorentz force. The Lorentz force is a force that acts on a charge q moving in a velocity v inside a magnetic field of strength b. The magnetic magnitude of the force is given by q times v times b. The direction of the force is given by the right-hand rule. When you point your index finger towards the velocity and your middle finger towards the magnetic field, the force will be in the direction of your thumb. Of course, you need to use your right hand. When the velocity of the charge is not perpendicular to the magnetic field, you need to use the more general vector product formula. The force is the product of the charge, velocity, magnetic field, and the sine of the angle between the velocity and the magnetic field. The theory of relativity says that if you move in a magnetic field, you experience an electrical field. The electrical field is given by the velocity times the magnetic field, or more generally as the vector product if they are not necessarily perpendicular. So now we have two descriptions of viewpoints of the Lorentz force. One is the force acting on charge in a magnetic field, and the other view is that if someone is moving in a magnetic field, in its frame of reference it sees an electrical field, and this electrical field is what gives rise to the Lorentz force. These are two different views of the same phenomena, and we're going to use the view that uses the electrical field. A reminder about the magnetic field of a current loop. The magnetic field lines shown in blue are from, we have a top and side view. They go from the center of the loop in closed orbits, and this is a result of Gauss' law of magnetic field. Field line must be always closed, unlike electrical fields, which must end at a charge. Note that the magnetic field lines are sometimes closed far away, and sometimes they're even closed at infinity, such as in the case of the field going in the center of the loop. In the case of an infinite solenoid, the magnetic field lines are parallel to the solenoid axis and they all close at infinity. So there's no magnetic field right outside the solenoid. There are formulas in literature on how to calculate the magnetic field of a solenoid, but we're just going to concentrate on the field and not on the sources that create the field. When you want to increase the magnetic field, you need to maintain all the field lines closed. So in order to bring new field lines into the solenoid, you have to bring them already as closed loops. How can we do this? Imagine that the blue arrows are the field lines and the field lines are coming into the solenoid. When viewed from above, you can see that the little field lines are going into the loop. When the field lines are moving relative to us, there is a Lorentz electrical field in our frame of reference. This electrical field is shown in green lines. The direction of the electrical field is given by the right-hand rule, as usual in the Lorentz force, and as you can see, it's going around the circle, always perpendicular to B and the velocity of the magnetic field lines. The electrical field is calculated in the following way. Suppose we're bringing field lines from outside. It doesn't really matter what the value of B hat outside. We just need to count how many field lines are crossing the circle per second. And this is relatively easy. We know that the field lines are moving in velocity v and they have a density B hat. So the number of field lines crossing the circle v times B hat, of course, times the circumference of the circle. And of course, when we are moving these field lines, we're creating the Lorentz electrical field as we discussed. Now, in order to actually calculate that electrical field, we can count the number of field lines coming into the circle in a different way. By counting the rate of change of number of field lines inside the circle, we know exactly how many field lines just got in. It's like counting the number of people that just came into a theater by counting how many people are inside the theater all the time and keeping track of the changes. This is of course equal to the change of flux inside, which is the area times the rate of change of the magnetic field inside. So we have the equation that the electrical field, the Lorentz field, times the circumference is given by the change of flux per unit time over the circumference of the solenoid. To summarize Faraday's law for changing magnetic field, the changing magnetic field induces an electrical field which is tangential to the region where the change took place, and this is valid for every region you take, however small it may be. The direction of the electrical field is given by the direction of the Lorentz force, and the magnitude is given by the strength of the Lorentz field, which is given by the Lorentz field formula. When we want to calculate an electromotive force in the loop which is surrounding a changing magnetic field, we can use the following reasoning. Remember that there is an electrical field going all around here and the magnetic field is changing. If we want to calculate the total voltage or the electromotive force in this loop between the two blue dots, we have to sum up all the electrical field going around the circle, and of course the field is given by the area over the circumference times the rate of change of the field, magnetic field. When we sum the field over this circumference, we just need to multiply the electrical field by circumference, and then we get the famous formula for the electromotive force, which is the rate of change of flux inside the loop. In the case where we close the loop, we actually make a short circuit here, and then we'll have some current running in the loop. The magnitude of the current is given by the electromotive force over the resistance of the loop. Let's use what we learned to solve some examples. The first example is a magnetic field which is changing in time but at a constant rate. So B is equal to some constant beta times the time t. We want to calculate the electrical field at some distance small r from the center of the solenoid. We want to calculate also the electromotive force induced on the loop going around the solenoid at some radius. Remember that in the case of the solenoid where the field inside is changing, but there's no magnetic field outside the solenoid, only we have a field inside. Let's first look in the case where the loop is outside the solenoid. The total amount of field lines or the total amount of flux coming into the loop is given by the area of the loop times the change of the magnetic field, and the electromotive force is given by the electrical field in this green dotted circle times its circumference, and of course it has to be equal to the rate of change of flux. When we have the second case, when we're inside the solenoid, the change of flux per unit time going into the green loop is given by pi times r squared times the change of the magnetic field. The electromotive force, again, is the electrical field times the circumference and is given by the rate of change of the flux inside the loop. So in the case the loop is outside the solenoid, the electromotive force is independent of the ring radius, and the electrical field is the EMF over the circumference, so it's going like 1 over r. In the second case, the EMF, which is the flux change rate, is growing quadratically since the magnetic field density times the area of the loop. And the electrical field is just growing linearly since it is the EMF over the circumference. As a second example, let's look at a slightly more complicated case of a section of a loop inside a solenoid with changing magnetic field, the rate of which we saw in the previous example. We know that the Lorentz electrical field is R times the rate of change of the magnetic field over 2. In this simple case, the Lorentz field is always parallel to the wire, so the EMF is the Lorentz field times the length of the wire. And we just studied the case where the E is parallel to L, but in the general case where the wire is not parallel to the Lorentz field, such as a straight piece of wire, we need to sum over all the sections of the wire, but only over the component that is parallel to the Lorentz electrical field, namely the tangential part. Well, an easier way to get around this, doing this integral, is to add two sections of a wire, shown here in dotted lines, that are radial, going from the center to outside, up to the wire. These sections of wire are perpendicular to the Lorentz electrical field, so there's no EMF accumulated on them. Remember that the EMF is the sum of the scalar product of the field and the sections of the wire, which gives 0 contribution because they're perpendicular. Now that we have a closed loop, we can use the standard formula for EMF, namely the flux rate of change inside the section that looks like a piece of pie or a triangle, depending on what shape of wire we chose. So to summarize the Faraday's laws for changing magnetic field, the changing magnetic field induces an electrical field which is tangential to the region where the change took place, and this is valid for every region you take, however small it may be. The direction of the electric field is given by the direction of the Lorentz force, and the magnitude is given by the strength of the Lorentz field, which is given by the Lorentz field formula. And this view is slightly different from the standard way Faraday's law is taught, so especially at high school level, but I hope it helped you look in Faraday's law in somewhat more local approach, meaning that the magnetic field affect only their immediate vicinity, and only when we sum up the total effect of the changing magnetic field everywhere do we get the familiar Faraday's law. Thank you for watching this video, and I hope you liked it. Please leave your comments or subscribe.